Okay, the title of my lecture today is the arrow of time in brain signals, and as we will see, is a new methodology or an alternative methodology for assessing causality, and in that way also for assessing the functional hierarchy in brain dynamics. The main idea, let me start with a very short overview of what is the main subject today. As I say, our main interest from the neuroscience point of view is to assess the functional hierarchy of the brain dynamics, of whole brain dynamics, under different circumstances for assessing the hierarchy or how the hierarchy change in different brain states, in different cognitive states, or even in different clinical states. The traditional way of assessing the hierarchy is to characterize, to quantify directly the causal functional interaction. And there are many ways of doing this. I will present in the next slide some, well, we'll remember you very briefly some possibilities using the concept of Granger causality or transfer entropy. Basically, what I will try to transmit today in this lecture is that we can assess the hierarchy indirectly by assessing these functional interactions as an observation of how the tail balance between those functional interactions is broken. So the idea is to capture the breaking of the detail balance, in other words, a hierarchy, by using a thermodynamic tricks. This is what we call the thermodynamics of mind. And it's a very simple idea, basically based on the fact that capturing the arrow of time indirectly is telling us something about how much the underlying balance, the functional balance, is broken. And I will basically dedicate most of my talk to explain this concept, to see how we can quantify that, and basically also to show some application and some results. And at the very end, I will relate this concept of arrow of time, of how we assess the breaking of the detail balance, which is also associated with the non-equilibrium, as a way of relating another features, which is usually concomitant to the non-equilibrium that we were characterizing in the first part, namely the fact that in general non-equilibrium is associated with turbulence. And I will say a couple of words about that, and especially to define and to use turbulence in the context of neuroscience as a way of assessing an efficient or to measure, to characterize the information processing, in which way the information processing is performed under different circumstances. Again, different type of cognitive states, brain state, and so on. So let me start just by being a little bit more concrete about what we mean with the hierarchy. One particular example is just to give you a flavor of what we mean with functional hierarchy. Can be thought in the context of the organization of the brain for solving many different cognitive tasks. And as you know, that was first formulated by Bars and then refined by Dehaene and Chanchot in many papers. It's associated with the concept of the global workspace, namely that there are an organizations of the different parts of the brain, the different regions, that they show different functional type of interactions, of causal interactions, and they are like an internal kind of club of or core or key regions, which are called the global workspace, which are namely orchestrating basically the hierarchical organization of the underlying computation. And this is the goal, to try to quantify and to try to discover in which way we can discover that particular organization or similar type of organization. In fact, I mean, we have done recently in a paper in Nature Human Behavior, we quantified this by using basically the concept of, refined concept of the transfer entropy as a way of measuring causality, and by measuring causality between the brain regions under different circumstances, for example, using the HCP dataset, which included not only resting state, but 7 different cognitive tasks, we were able to analyze this functional organization in each condition, and by performing the intersections and how we were getting access to this concept of the global workspace. So that's, we get in a quantitative way some information about this orchestration of the functional activity. What we are presenting here is an alternative, and actually it's motivated by a key idea that was discussed and proposed a lot by many people in physics. I just took here my favorite book that was reading during the pandemic, the book of Schrödinger, What is Life, where basically he stressed the relevance of the concept of arrow of time and the concept of non-equilibrium in biology. In particular, that was this concept was already used in the context of neuroscience. There was a paper by Christoph Lin from the lab of Danny Bassett, which was explicitly using this concept that I mentioned very briefly at the beginning, namely that if you have a system, whatever system you can imagine, with interacting, in this case could be the brain or the system of interacting spins, a physical system, if we have interactions, causal interactions, which are extremely balanced, then the system we know is in equilibrium. There is no irreversibility, so the production entropy is 0, and there is no arrow of time. On the other hand, if we start to break the symmetry, then the production entropy increases. So the production entropy is a measure, as a quantification of the arrow of time, of the level of non-reversibility, and that level of non-reversibility in turn is a characterization of the underlying breaking of the symmetry, in other words, of the underlying formation of a hierarchical organization. And they use that and they quantify it in some way, the production entropy, and they were able to show that that is different under different conditions, for example, rest and task. So we will use these conceptual ideas just to give you a more concrete flavor about that, about the concept of the arrow time. I am showing here a piece of this movie from Christopher Nolan called Tenet, where you see very, very easily in this case, in the macroscopic case, that there are some people in this movie which are moving forward in time and some people moving backward in time. So it's very easy and intuitive to know who is who. I mean, on the other hand, if you see this other movie, this is a real system, a simulation system, sorry. It's an spin system that we took from the paper of Saif et al., Jasinski paper, also using these ideas of arrow of time in physical system. And what you see is one of the observables on that particular microscopic physical system. And one is showing the evolution in time of this observable in the forward direction, and the other is the reversal, so the backward reversion, exactly like in the movie. And in fact, we cannot distinguish. And to be honest with you, I don't remember who is who. But that means that sometimes in the macroscopic case, it's very easy to detect the arrow of time. And in other cases, like in microscopic cases, or in the cases of brain signals, we will see soon, it's not so easy to distinguish, in spite of the fact that we know that there is a clear arrow of time. There are other cases where we can see that the determination of the arrow of time is very easy. For example, in again, a macroscopic system that is clearly non-reversible, that is a bullet shutting on a glass of wine. And basically what we see here on the top is the forward movie, and then the reversal, the backward movie, and it's very clear to distinguish which one is which. So that means that it's very clear to associate an arrow time to this condition. On the other hand, if the system is macroscopic, but in this case perfectly reversible, so we have just this collision between those billiard balls, which are elastic collisions. Then we are showing here again the forward and the backward movie, but we cannot distinguish them. And this is due to the fact that there is no arrow of time here because the system is in fact absolutely reversible. So the key idea then is just summing up the concept that we presented is really to try to measure this level of non-reversibility in order to assess the underlying level of a hierarchy, so to assess the breaking of the detail balance. And there are two ways of characterizing this non-reversibility. One is directly by trying to characterize in a quantitative way if there is an arrow of time, and the other is by assessing the increase of the production entropy. And that, as we will see in some cases, or as we have already seen in the macroscopic cases, very easy to distinguish the forward and backward evolution. In some other cases, it's not so simple, and therefore we will need to use some special methodologies for trying to extract directly the arrow of time. Actually, our approach, or the approach that we will present now, is not to measure directly the entropy production, but to try to assess this arrow of time by comparing the forward evolution and the backward evolution of the brain signal. And this is what we are showing here. We can take the brain, our favorite measurements and characterization of the brain signals. And for example, just to keep this simple, let's assume that we have a ball signal in one particular region, and this is the natural evolution. This is what we measure. We can artificially flip basically the time and generate the time reversal of the backward version of that particular signal. And given that we are constructing this by hand, we know who is whom. So we know who are the real brain signals, and we know which are the signals that we reverse it by hand. And then we can train a classifier. In particular, we will train a deep learning classifier in a supervised way because we know the labels of the signals. And basically then checking how good this classifier is, we can assess if those signals, they were really distinguishable, meaning if there is an arrow of time or there is no arrow of time. So if the performance of the classifier is high, then we can claim that there is an arrow of time and the system is non-reversible, and there is consequently, concomitantly, high level of non-equilibrium. On the other hand, if it is low, then we have reversibility and equilibrium. So we can do that at different levels, as indicated here on the right, at the global level. So take all the whole brain signals in a given parcellation, or just restrict to networks, or even to go to the local single node level. The classifier that we use, as I said, is a deep learning classifier that we call Tenet, in honor to the movie that we already mentioned from Christopher Nolan, but in this case is a temporal evolution deep learning network. And basically what we do in all these different cases, we define the signals in different sliding windows in order to reduce the dimensionality of the input data. And at the same time, we assess the level of non-equilibrium, non-reversibility, and the level of non-stationarity by doing this trick. So in each sliding window, we apply this trick of flipping the signal, generating and training and generating the forward and reversal version of the different brain signals. I will show just one, in interest of time, just one result, which is related just with the global analysis of all the signals. Of course, you can read in the written version of the corresponding papers, the analysis of the network level and the node level. But just to give you now a concrete feeling of what we get, this is the HCP, human connectome data associated with the resting condition and the 7 different cognitive tasks that they measure. As you know, it's bold, ephemerized signals, large sets of subjects, over 1,000 people. And what you see here for all these conditions and all the different subjects, the level of non-equilibrium of the level of non-reversibility. And you see very clearly that resting is, of course, non-reversible, but it's the condition with the lowest non-reversibility, and the different tasks are showing an increasing level of non-reversibility, which makes sense from the point of view of non-equilibrium, because of course the brain is much more driven from the environment. But what is even most important for us, the brain for solving that particular condition, for computing those particular tasks, has to be much more structured, has to show a much more asymmetric type of hierarchy, meaning or reflecting a deeper breaking of the underlying detail balance. And that is exactly what we are characterizing in this indirect way with this measurement. Here, of course, you see the result on the sliding windows, the variability of this level of reversibility across time, reflecting the different level of non-stationarity. And it's also useful to see that depending on the condition, we have significant different level of non-stationarity. Of course, I mean, the training of the deep learning network is a complication, it's time consuming, it's very, very reliable, but we can simplify the methodology just by using exactly the same concepts, but assessing the measurement or the quantification of the arrow of time in a much more simple way. And the key idea, the key trick is shown here. Again, we will compare the brain signals. So we are not using the production entropy. We just assess the brain signals in the forward and the artificially created backward version. But for example, let's just consider now a pair, just 2 brain regions. We can characterize in a cheap way, let's say, so the causality by shifting the signals in the forward version, shifting by a given time capital T. And of course, this is a kind of cross-correlation, of shifted cross-correlation, which is showing in which way the causality is reduced when we increase the shift. If we do this now for the backward version, and we calculate again this shifted correlation, and we can compare for a given shift, for a given capital T, these 2 situations, given that the shifted correlation is breaking the symmetry in the time, and we are comparing the forward and the backward version, the comparison of that correlation of the forward and backward is a measure of the level of non-reversibility, a very simple measure of the level of reversibility. As you see here, we are not obliged to take a sliding window so that we can use all the data for a very robust estimation of the correlation. And also we don't have to divide and to lose part of the data in order to define a training set or a validation set, as we were obliged to do that in the case of using machine learning techniques. So from that point of view, it's much faster and much more robust. Of course, the disadvantage, this is limited to pairwise type of characterization of non-reversibility. Of course, nevertheless, we do this at the whole brain level. We take all the pairs. So for that, we define a matrix, which is basically the shifted correlation for all pair combinations for the forward and for the backward version, and basically comparing these matrices, we get exactly a number at the end of the day, which at the global level is characterizing the level of non-reversibility. Just to give you a flavor of the possible results that you can get with that, well, of course, we applied that also to the HCP, and we got a very consistent result with the first version of the way of analyzing the arrow of time, namely Tenet. So a difference between cognitive states and racing state. We have also applied to fMRI data in different brain states like deep sleep and awake and so on. But in this case, I will show this totally different species of our data on monkeys, which are publicly available in a site called Neurotyco. They are ECOG data in half hemisphere of four monkeys under different conditions. For example, awake against sleep or awake against anesthesia and different type of anestheticum, and even the recovery. So they are beautiful data. It's a different type of brain signal. Now it's not ball, it's an electrical signal, and then we will see the results. Basically, this is the main figures reflecting the main conclusions. First observation, if we try to separate the different conditions, you see here, sleep or the different anestheticum, so sleep against awake or awake against propofol and recovery, just with the functional connectivity, just with the normal correlation, we don't see a clear separation. And this is reflected here just in form of the matrix, here in form of the scatter plots. Nevertheless, if we measure the non-reversibility, as we described it before, just by this comparison between the shifted correlation in the forward and the artificially generated reversal version, we see that under different conditions, this is for a particular trial of a particular monkey, in the different conditions, sleep, awake, or wake, and anestheticum, we see a clear differences. Even the recovery is very well reflected. Of course, in order to have a statistical significance of this result, we can see this at the global level. So over all monkeys, all the trials, and then we see that in all cases, we have a significant differences reflecting different level of non-equilibrium, reflect different level of non-reversibility, or in other words, reflecting what is more important for us, this different level of breaking the details balance or different level of hierarchical organization. Just in order to finish my lecture today, I want to stress one point, which is very interesting per se. The fact that we have non-equilibrium and non-reversibility, as we already commented, is extremely interesting to assess the hierarchy, but it's also revealing another fact, namely that in most of the cases, non-equilibrium systems are showing a very particular dynamic, which we call turbulence. In fact, the word turbulence was created by Leonardo da Vinci. In Italian, turbulenza comes from the Latin turba, which means crowd. And he was very much interested in that because he was really astonishing, really this combination between randomness, stochasticity, and ordering. And in fact, he was trying to capture this mixture between order, like you see here in this vertical vortex structures, and the underlying kind of stochasticity or randomness. In fact, I mean, as you can imagine, people that in physics got very much interested now, not only from an artistic point of view, but really try to understand this very particular case of chaos, of spatial-temporal chaos, where we see this really astonishing combination of stochasticity and structure. In fact, that was reflected, and a key observation of that particular hierarchical organization of the structure was done by that person that appear in between that we will see again in the next slide, that has done a very clear observation that the size of the vortices, which by the way was also observed by Leonardo da Vinci, but he formalized it, that they are hierarchical organizing. So meaning that somehow the largest vortices are feeding the intermediate vortices, and they are feeding the more smaller and smaller vortices. In fact, he used this poetic form, was a paraphrasing of the Jonathan Swift Siphonaptera, expressing basically this hierarchical organization. That was very inspiring, because then Kolmogorov, a genius, as you know, took this idea and associated this hierarchical organization of the sizes of the vortices as an indication of a very effective transmission of information and energy. And he was able to show that from a phenomenological or from a statistical point of view by using a very key and simple concept that he called structure functions. It has nothing to do with what we call a structure or function in the context of neuroscience. But as you see, it's a very simple concept. It's just the quadratic displacement of your variable. In our case, will be our brain signals, for example, Paul. And this, I mean, actually, if you decompose this, you immediately discover that this is a Cousin of the functional connectivity. This is just the correlation between in two different spatial positions shifted a given distance. And note that the distance is not a vector, so meaning that it's isotropic and homogeneous. So it's the functional connectivity, but now observe it under that perspective, that is not in just a given parcellation, but it's a functional connectivity as a function of the underlying distance. In fact, Kolmogorov was able to show very nicely that if you take this structure function or the functional connectivity as a function of the distance, he discovered a power law. When you have a turbulent regime, there is a power law that reflects exactly this efficient transmission of energy that he also measured directly, and in a particular region that he called the inertial subrange, by the way, or this power law, this efficient transmission of information by using the correlation. A key concept for trying to apply all these ideas in the context of neuroscience is based on another genius that is Kuramoto, that basically found a way of extending the concept of turbulence to a non-hydrodynamic system, which is in our case, for example, the brain. The idea is very simple. He just generalizes the concept of the global Kuramoto order parameter. As you know, the global Kuramoto parameter is just the sum in this case because it's continuous. It's the integral of the exponent imaginary part of the phases. And the module of that, which is R, is just a number between 0 and 1, which is given as a quantification of the general level of synchronization. In this case, I mean, he introduced a weighting factor, so that which has an exponential form, and we get the generalization of this global Kuramoto order parameter in the sense that now we stress the locality. So therefore, we can assess now the level of synchronization, not only as a function of time, but as a function of the location. This is for a system of coupled oscillators, where he's showing that how that works. And what we see here, that as a function of time and as a function of space, the level of local synchronization, and that is the key idea, is changing a lot. And basically, when this level of local synchronization has shown a large variability across space and time, what we call metastability, and what we use it a lot in the context of neuroscience, but just using the global concept of metastability. So characterizing the global level of synchronization and just observing the variability across time. Here is a generalization that now we include the space. And basically, we can name, or we can associate turbulence to a system when that level of variability, as is reflected here, just in a pictorial way, is very rich. So, and those local level of synchronization that are changing across space and time are reflecting this vertical structure in the system associated with turbulence. In fact, we measure this again on the HCP, just concentrate on this picture. This is exactly the variability of the local Kuramoto order parameter in the real data under resting state condition that you can compare with the corresponding surrogate just to assessing the level of significance. Just to give you a more concrete feeling, I mean, if you take a snapshot of the phases that you can extract from the Ball signal, by the way, we use it here, very fine parcellation, the Schaeffer 1000 parcellation, in order to have access to the to a relatively accurate distinction of the distance between the different parcels. So what you see here are the 1000 nodes of the Schaeffer parcellation, the corresponding phases at the point in time for different snapshots. And what you see in the case of the real data of a particular subset, particular session, that's this type of clustering of the phases, which is reflecting really this different level of local synchronization, so the different vortices. And those vortices and the variability of those vortices across space and time is reflected in that very positive, significant value that means that the system is turbulent. We can even model that. I'm not showing that just in interest of time. If you compare that with the associated surrogate, then you see that there are nodes that particle structure. So this is the what they call the Hollywood version of that. It's just the rendering of the local Kuramoto order parameter for a particular subject of the HCP data set, and showing across the space and across time how this different level of local synchronization is changing. So meaning how this generalized concept of metastability is very high. Just to finish, I mean, let me give you an idea that this concept of generalized local metastability or turbulence could be used in order as a biomarker in order to study the dynamic of the system. For example, this is just a very particular example for distinguishing different brain states. What you see here is the different level of turbulence and different concept, information theoretical concepts that can be defined according to the basic concept of turbulence that I am not describing now in interest of time. But just if you concentrate on the level of turbulence for these different conditions, there are different coma patients, and they are showing under the different condition, if it is a vegetative state, minimal consciousness, or the control group of subjects, then we have a significant different level of turbulence. The same happens in awake when you compare this with deep sleep, or even in much more really subtle cases where the dynamics is just distinguished by the level of meditation. Even more, if you analyze the level of turbulence at the network level, again, for meditation, sleep, and the coma states, and here we added also other manipulations, which has to do with the experiment of Robin Carhart-Harris, where he manipulated or he administered to the subjects, to healthy subjects, different type of psychedelics like LSD or psilocybin. And the beauty is that to see in all this manipulation of consciousness or unconsciousness on the top, in particular, you see that in spite of the fact that behaviorally you have the same, I mean, they are unconscious, but there is a very particular fingerprint underlying that particular situation. So I just finish here. I hope that I was able to transmit that using these thermodynamics tricks, these conceptual, very important conceptual ideas of arrow of time and relating the arrow of time with the underlying hierarchy, we gain information about the functional orchestration and the different circumstances. And concomitantly, because this is associated with turbulence, we get a way of developing biomarkers, extra quantification of the brain dynamics, which characterize directly from another point of view, the transmission of the efficient transmission of information that describe the different brain states. This is my friend and colleague, Morten Kringelgebach, with whom I developed all this idea. So thank you for your attention.
Fantastic.
It's okay?
Yeah, that was beautiful.